we can now consider how we can use electropotentials in a practical way. So let's go back to our hydrogen standard electrode with magnesium. And we noted in the previous video that if we performed this experiment, we would see a reading of minus 2.37 volts on our voltmeter. Okay, so what does that actually mean? Well, in order to be able to show this, and so I can explain to another reader how I've got to minus 2.37 volts, I use cell notation to show which electrode is on the left and which electrode is on the right. And the way we write that is the left-hand electrode, funnily enough, is written on the left-hand side with the red circle there, and the R is the reduced species and O is the oxidized species. And then when we go to the right-hand cell, the O is the oxidized species on the for the right-hand half cell, and R is the reduced species for the right-hand cell. And the double line is a salt bridge. And these two single lines represent a phase change. So, okay, let's look at the right-hand cell. So if we were to show the right-hand cell using that cell notation, the oxidized species is Mg2+, the reduced species is Mg solid, and our left-hand cell, the reduced species is H2, and the oxidized species is H2. But we do have another issue that we haven't shown the platinum electrode for that. So we need to add an additional piece of information, and we do that by adding PT and then another phase change toward the left-hand side. So if we were to show that, we would quote our standard cell potential as being minus 2.37 volts, and we use the little funny circle with a line through it as demonstrating that that experiment or those results would be obtained under standard conditions. Look at a few different examples. So we are going to try and work out the cell potential of that cell written there. So it's the silver solid Ag plus and the Fe2 plus to Fe. So let's find those in our table. So Ag is there and gives us a value of 0.80 volts, and Fe is there and it's a figure of minus 0.44 volts. And the way we work out the cell potential is it's a right-hand cell potential minus a left-hand cell potential, which is minus 4.4 minus 0.8, which gives us an overall cell potential of minus 1.24. So what does that figure actually tell us? Well, that shows that that would be the cell potential of silver solid going to Ag plus and Fe2 plus becoming iron, and relates to the reaction shown there. So silver reacting with Fe2 plus to give me silver ions and iron metal. And the negative cell potential says that reaction is not feasible. It is unlikely to happen, and it won't happen. So if I was to add some silver metal to some Fe2 plus ions, we would not see a reaction. However, if we were to reverse the reaction, so we reverse the cells, so the iron is now on the left-hand side and the silver is now on the right-hand side, we now have a cell potential of plus 1.24 volts, and that refers to Ag plus ions reacting with iron metal to give me iron 2 plus ions and silver metal. And the positive figure represents that reaction is feasible. So if I were to add iron to a solution of silver metal ions, a reaction would occur. And that makes sense from our reactivity series. Now, these predictions are great. We just need to be a little bit careful. Any cell potential which is greater than plus 0.3 volts, it will proceed even under non-standard conditions. So even if we start changing concentration and temperature, however, this gives us no information on rate. So it could be completely feasible energetically. However, it will take an age to occur. Um, the other issue is that if we start changing our concentration, that changes our cell values. So if we look at a half equation for silver plus an electron becoming silver metal, and we said that that was plus 0.8 volts under standard conditions. Now let's say I now change that cell and I decide to increase the concentration of silver ions from 1 mole per decimeter cubed to 2 moles per decimeter cubed. And that would make the equilibrium shift to the right if we use Le Chatelier's principle. So if we to do that, and the equilibrium shifts to the right, the number of electrons on the metal will decrease because the electrons are on the left-hand side, and if it shifts to the right, the number of electrons will decrease, and because the number of electrons decreases, the cell will become, that cell potential for silver will become more positive. And therefore the overall cell potential with Fe becomes more positive. So why would we bother to separate these two reactants? So let's go back to this reaction and think about what's the point of doing all of this? Why don't we just mix iron metal with some silver plus ions and let the reaction proceed as normal? Why are we separating them by putting them in different beakers? Well, we're effectively making a battery. If we just add them together, it's quite right, a reaction would occur as that. However, by separating them, we can make the electrons transfer via the wire. So, how does that occur? So, if we have a look at the cell, you will see that the iron electrode potential has a value of minus 0.44 volts. So we would class that as a negative part of the cell. And the silver is plus 0.8 volts, and therefore that is the positive part of the cell. And as you know, electrons are negative, and so electrons would flow from the iron electrode to the silver electrode. And by doing so, we've created a battery that has a voltage of 1.24 volts.